So I want a new, better computer. And I promise I'm not just saying that because I broke my personal computer during an ill-advised stretching session at my desk last week. Full disclosure, I did do that, but it's not why I want a better computer. I want a better computer because we are frustratingly, tantalizingly close to breakthroughs in many areas of science, but we're being held back by our computer technologies. We know how to ask computers to help us design new cancer treatments, better solar cells, better batteries, but we haven't done it because we know that these programs would take hundreds or thousands or millions of years to run. And to put that in context, that's longer than it feels like the current presidential election has been going on. It's unacceptably slow. What we need is something new. We need a breakthrough in computing so that we can reach these other breakthroughs, and physics might be able to help us with this. You see, the way that we compute things right now is a little bit old-fashioned. What we want to do is explore some alternatives. The laws of physics on a really small scale, we're talking molecules and atoms or smaller, are radically different than, seem radically different than they do in large-scale life. And so if we could build a computer whose components were individual atoms, it would have radically different capabilities. And let me give you a concrete example. Many important computer problems involve searching for one solution out of many. Maybe the computer knows all the millions of possible configurations that a molecule could take on, and you want to find that one special configuration that can function as a new drug. Well, a regular computer has to search for that the way a regular policeman searches for a suspect in a high-rise apartment, one room at a time, and that's not efficient. But a quantum computer would not have this limitation. Thanks to something called quantum superposition, it can think about all the possible solutions simultaneously, a little bit more like Superman, who could use his X-ray vision to see everybody in the apartment all at once. Now, sometimes people take this metaphor a little too far, and they think this means that a quantum computer could instantaneously solve these problems, and that's too good to be true. Think about it with Superman. Even if he can see everyone, he can't tell where to focus his attention right away. But if he knows that he's looking for a man, he can start to ignore the women. And if he knows he's looking for someone tall, he can start to ignore the short people. He knows he's looking for someone humble, so he can ignore all the Kardashians. You know it's true. And after a few steps, he's zeroed in on the person that he's looking for. A quantum computer works the same way. It starts with all the possibilities, and then the atoms are finely tuned until only what we're looking for is left. So when I say I want a more powerful computer, I don't mean a more powerful supercomputer. I really mean a computer with superpowers. If we can harness the capabilities of quantum physics, we can achieve huge breakthroughs in computing that will lead to breakthroughs in all areas of science. And I promise if we do build one, I'll do my stretching as far away from it as possible. Thank you very much.
You know, I've been around a while, and I keep watching as computers get smaller and smaller and smaller, and now we've got things that are actually embedded in your skin that, you know, are these fascinating computer things. So the quantum computer, is this going to have that same capability? Is this something that could literally be, you know, teeny tiny, or is it the old?
That's a great question. There's a kind of an irony to this, and the magic of a quantum computer comes from the fact that its constituents are themselves nearly subatomic, but the difficulty right now of manipulating subatomic particles means that the quantum computer itself is very large, at least with current technologies. So you have a handful of individual atoms, and then an enormous system for keeping them cool, an enormous system for shielding them from electromagnetism, a bunch of lasers that hold the atoms in place. At the moment, it's actually a large-scale technology that harnesses small-scale physics.
So, quick question. How do you feel about Trudeau? Did he get this right?
I think Trudeau did very well for a politician, and I wish that the leaders in our country were as
That's a very cagey compliment there.
It's very difficult to say everything correct about quantum physics. Maybe he was in some superposition of correct and incorrect, but he did quite well.
Nice. So you said something interesting that I wanted to go back to, and that was that these quantum computers were going to use atoms as, and
sure.
You know, I'm pretty sure the computer I have now is made of atoms.
It's made of atoms. It's made of too many atoms. It's made of so many atoms that they all interact and interfere with each other and sort of destroy their quantum, important quantum properties. If you want to make a quantum computer out of atoms, you have to isolate the atoms from the rest of the universe and allow them to interact only in small groups. I should say using individual atoms as the constituents of a quantum computer is only one of several very promising proposals for how to build a quantum computer. Any device that's small enough it can capture that it can capture the quantum, I think it's okay, thanks. And any device that's small enough that it can exhibit some quantum behavior by acting on a single particle level, that kind of thing, could work. But I think it's easiest to visualize with atoms, so I like to use that as my benchmark.
So we often hear about Moore's law,
Sure.
Which I guess isn't really a law, but a trend where processor speed doubles every so many years. And then we're always hearing that Moore's law is reaching its end because things are physically not going to be able to keep doing that. And then we sometimes hear about this other kind of computing that is hopefully close to being a reality, quantum computing, which I don't really understand, but after your talk I do somewhat more, so thank you.
Good.
But my question is, how does that fit into Moore's law? Is it going to be some jump forward in that trend?
So I think it's important not to overstate the capabilities of quantum computers. We're still a little unsure how they would compare to regular computers, but one thing we know is that they would be radically different. There are certainly some problems that they could solve enormously faster than regular computers. There are other problems where we suspect they would be no better. There may be some problems where they would actually be worse than regular computers. So at the moment, as far as I understand, the best proposals for how to harness the capabilities of quantum systems is to couple them with regular computers. Take advantage of their capabilities where they're most useful, and then resort back to the classical computing that we've been perfecting over the last 100 years when it's more appropriate to do that. So I think the idea for circumventing the Moore's law boundary there is to create something synergistic between these two phenomena. Thanks. Thank you.
Thanks, Colin.